Next, exercise 5. In this one we have V as usual, a finite dimensional inner product space, and we are given an orthonormal set of vectors in V, these Wi's, this m number of Wi's, such that additionally this condition is also given. That is, if we consider the squares of the absolute values of these inner products of V with the Wi's and take their sum, then that is equal to the square of the norm of V, and this happens for every vector V in V. If all these things are true, then we have to prove that this set is in fact a basis of V. Now, one thing we can immediately conclude about this set is that it's a set of linearly independent vectors. That's because it's orthonormal, so any orthonormal set is a linearly independent set. But we have to prove that it also spans V. So what now we are going to do? We are going to remove from the vector V all its components along the directions of this Wi. You will understand this remark when I define this vector. In fact, this is what we did in the previous exercise. For any V in V, we define the vector u. That is, what I said just now is that from V we are going to subtract all the components of V along the directions of these vectors. The component of V along the direction of W1 is this. Alright. The magnitude of the component is this. I mean, these terminologies are just for us to understand. It's an analogy. Okay, these are not actual physical vectors. These are just some elements in a vector space, but by analogy we can say such things. And we continue removing these components. Okay, so let this be our vector u. Then we already did something with this vector in the previous solution. So then by the solution to the previous exercise, we have this. The square of the norm of V is equal to this quantity where I varies from 1 to m plus the inner product of u with itself. And in fact, this is what led to the that Bessel inequality, right? So we proved the Bessel inequality in the previous exercise. So in the course of proving it, we came across this identity. But now what is given? It's given that this thing is equal to the square of the norm of V. So by our hypothesis, that is this part, the inner product of u with itself is 0, and hence u itself must be equal to 0 from properties of, the axioms that we have in the definition of an inner product. This is 0 if and only if u is 0. So u should be 0. But if u is 0, then v will be equal to the linear combination that you see here. I mean, take all the things on the other side. Thus, V is this linear combination. But if V is the linear combination of these Wi's, then V belongs to their linear span. However, V is any vector in V. So any vector belongs to the linear span of these Wi's. So the Wi's span the entire space. So V is equal to the linear span of this set. Since this set, being an orthonormal set, is also linearly independent, it's a known result, but still, if you want, you can refer to where it's coming from by lemma 444. It is a basis of V, and that's what we wanted to show. So this is the solution. Next, exercise 6. If the dimension of V is n, and if again here also we have a set, this is an orthonormal set. In V, then we can extend this to create a basis for the entire space V. We can extend this orthonormal set by introducing extra vectors if necessary. Prove that there exist vectors this in V such that the resulting superset obtained by introducing these new vectors is also an orthonormal set, and hence it's a basis of V. Okay, so now the dimension of the vector space is n, and it's given that this is again, just like before, an orthonormal set of vectors in V. We have to prove that there exist extra vectors if necessary, so that this resulting superset is also an orthonormal set, and hence it's a basis of V. Okay, Now in the solution, in the beginning itself, we can say something about the relationship between n and m. You see, here is the thing. You know two things already. One of them is that in an n-dimensional vector space, any linearly independent set can have at most n elements, not more than that. Okay, that is one thing. And the second thing is what we have seen here by lemma 444. We know that any orthonormal set is linearly independent. So that means the number of elements in this linearly independent set cannot exceed n. So m has to be less than or equal to n. So by lemma 444 and so lemma 444 says that this is a linearly independent set, and that other result, it is lemma 424, which says that in an n-dimensional vector space, any linearly independent set can have at most n elements. So by these two results, m has to be less than or equal to n. Now if m is equal to n, it may happen then there is nothing else to do, we are done. And that's why let's assume that m is strictly less than n. Okay. Now you recall a result that we saw in the theory of vector spaces itself, not specifically for inner product spaces, but just for finite dimensional vector spaces. Namely, that if you are given a linearly independent set of vectors in a finite dimensional vector space, then you can introduce extra vectors to enlarge that given set into a basis. Okay, now that just simply will be a basis. Okay, that need not be orthonormal. We have to fix that afterwards. So we are now going to, and that result is lemma 425 by lemma 425 there exist vectors, say we are not of course going to call these new vectors W, but let's call them Vn in V such that this new extended set obtained by introducing these extra V's to the existing set is a basis of V. But note also carefully that in order to apply this lemma, in order to be able to apply this lemma, we should start with a linearly independent set, right? But this part of the set with which we are starting is already linearly independent. Why? Because it's an orthonormal set. So by lemma 444, it is linearly independent. So we can start with it and we can introduce some extra vectors to complete a basis. Now we apply what we did in proving that result, which says that any finite dimensional inner product space has an orthonormal set as a basis. So we did something in the proof of that result, right? and we have given it a name also. It's called the Gram-Schmidt orthogonalization process. So we are going to do that here now. So for that, what we are going to do, we will subtract from Vm plus 1 its components along the directions of these Wi's. Let us call that vector um plus 1. It's defined to be equal to Vm plus 1 minus the component of Vm plus 1 along W1, and like that it goes. Finally, the component of Vm plus 1 along Wm. Yeah, these things can confuse you sometimes if you are not careful about these indices. Now there are two things that one can note about this um plus 1. The first thing is that this um plus 1 is not equal to 0. What would happen if this is 0? Then Vm plus 1 will be a linear combination of the Wi's, W1, W2 up to Wm, but then Vm plus 1 will belong to the linear span of these first m vectors. But then how can this set be a basis? Because in a basis all the vectors are linearly independent. If this is 0, then introducing Vm plus 1 to this set will give you a linearly dependent set. Okay, so that should not happen, because already we know that this is a basis of V. So note that we are not, of course, going to write all those things in detail. Instead, that is something we should already know. Okay, so we simply write, note that um plus 1 is not equal to 0. And we also know something else from a previous result. Have I written okay, let me write like this. Also, just like the proof of theorem 442, it is that result where we prove that every finite dimensional inner product space has an orthonormal basis. And if we go back to the proof, there you will see that a vector defined like this will be orthogonal to all the Wi's. That is, we have this um plus 1 and Wi. If you take their inner product, you are going to get 0. For all these i's. I once, while discussing these things, I once tried to make the analogy of this inner products being 0 with actual physical vectors, but I failed, I messed up, right? Do you remember? So I can do it now. It is like if you just simply think of this thing in terms of what we were saying, okay, that is, from Vm plus 1 we are removing the components of Vm plus 1 along the directions of these other vectors. You can imagine the situation like this. Say this is your x direction, y direction and z direction, right? And you have the unit vectors along these directions, I cap, j cap and k cap. Now say you have a 3D vector, something, say anything, I plus, to keep things simple, let's just take I plus j plus k. Say it is this vector. So what we are saying here is that you think of this I plus j plus k as Vm plus 1. Now what we do, if we subtract the components of this vector along the directions of I cap and j cap, say, then the component of this vector along I cap is what? It's just simply I cap. And we also subtract the component of this vector along j cap. Then you are left with k cap, right? And k cap is in this direction. And once you have that, then this, whatever you are seeing here, that is this um plus 1 in place of k cap. So you can see that this k cap is perpendicular to both I cap and j cap, orthogonal to both I cap and j cap. That's because since we have removed the parts of the vector along these directions, so now after that removal, if you look at this vector, it has nothing to do with those directions, and that's why it becomes orthogonal, just like your ordinary 3D vectors. But anyway, it also happens algebraically in general, so we now have this. Okay, so now we have the vector um plus 1, which is orthogonal to this first m vectors that were already given to us, which among themselves are orthonormal. Fine. But um plus 1 itself may not have length 1. To fix that, you divide it by its norm. Now and that's what we are going to call Wm plus 1. Wm plus 1 by definition is this. Note one more thing, that you are able to, we do not normally say dividing a vector by something, but we say multiplying the vector um plus 1 by the reciprocal of the norm of the vector. And this is non-zero because this is non-zero, and that's why this is possible. Okay, Wm plus 1 is well defined, it is meaningful. We thus get the larger orthonormal. See, orthogonality of the set that you would get from the original set, that is the Wi, by introducing this extra vector. Orthogonality is already there. Already the Wi's are orthogonal to one another among themselves. But now this one is also orthogonal to all the W's. That's what we have written here, right? All these inner products are equal to 0. But now for orthonormality, which all the previous Wi's already have, that is all of their lengths are equal to 1, that now is fixed by considering not um plus 1 itself, maybe it may have unit length, then you would get 1 here. Otherwise now we have Wm plus 1, which must have unit length. So that's why we now get this orthonormal set. Okay. Now, continuing this procedure, do you see how we are going to continue this now? We are now going to continue the procedure with this new orthonormal set which has one extra vector. We get a still even larger orthonormal set with yet another extra vector. That means to the original set we add two extra vectors, and this of course can be continued as long as we have orthonormal, as long as we keep getting orthonormal sets. That is, the current orthonormal set will look like this with one more vector. Now, will there be an end to having these orthonormal sets? Of course there will be, because we already know that any orthonormal set is linearly independent. Since the original space has dimension n, so the size of this must not exceed n. So until we get to n, we can keep on going and we will continue to have orthonormal sets. This way we eventually get an orthonormal set having exactly n vectors. And when we do that, what is it that we have got? By the time we get this, we have got a linearly independent set of n vectors, but then in an n-dimensional space, such a set would be a basis. We already know that from our previous theory of finite dimensional vector space. So that's why this is also a basis of V, which is just a remark. Mainly we have to show that such a set exists, which is obtained by extending the original orthonormal set. So that is the solution. And let's see another one. Use the result of this previous exercise exercise 6 to give another proof of theorem 443. Okay, and I need ink first. Theorem 443, if you recall, is that theorem which says this. Suppose you have a finite dimensional vector space V. Okay. In V, you have a subspace W. Then V is the direct sum of W and W perpendicular, its orthogonal complement. We already have the theorem, we also have its proof, but now we have been asked to again prove it using the result of that previous exercise. So let's see how that can be done. Okay, so here the thing goes like this. Let me start it from this side. We are not going to repeat the hypothesis that is there in that theorem. Okay, we already know, so let's just simply start the solution. Being a subspace of a finite dimensional inner product space, which is V, of course. V is our finite dimensional inner product space. We have V and W in the hypothesis of this theorem. That's what I said just now. We are not going to repeat those things. W is itself a finite dimensional inner product space. Well, how are we getting this? It just simply comes from this. We already know that any subspace of a finite dimensional vector space is a finite dimensional vector space. And additionally, if you restrict the inner product on V to W, it then turns into an inner product on W. So that's why we have this. Now, being a finite dimensional inner product space, W will have an orthonormal set as basis. We already know this result, and I keep forgetting the numbers of these theorems or lemmas. It's not possible to remember also. Yeah, by theorem 442. So, by theorem 442, W has an orthonormal basis, this. Okay, which also means that we are assuming that the dimension of W is M, small m. And so by the previous exercise, we can extend this to a basis for V, which also is that extended set also is an orthonormal set. By the previous exercise, he has an orthonormal basis, this, which is an extension of the orthonormal basis of W. So this fact also includes, it's a consequence of this fact that the dimension of V is n, small n, and the dimension of W is small m. Okay, there is no need to write those things separately. Alright, now you watch this. You see, because every vector in V, in our capital V, is a linear combination of these vectors, one part of that linear combination is a linear combination of this first MWYs, and they form a basis for W. Okay, so that means V is a sum of W and the linear span of the remaining vectors. This is a subspace, this linear span is also a subspace. Okay, and because every vector in V is a linear combination of the basis vectors of W and these extra vectors, so V is equal to this sum. Now, what is our original claim of the theorem that we are now trying to prove? The claim is that V is equal to W plus the orthogonal complement of W. So that means now we have to show that this L of this is actually equal to the orthogonal complement of W. So that's why we claim the orthogonal complement of W is the linear span of these remaining vectors. And now we will prove this claim. What we are of course going to do is we will show that each one of these spaces is contained in the other. One containment is almost immediate, since one containt is almost immediate, I am saying, but suddenly I am a bit confused about that. Oh yes, okay, yeah. Since these vectors are already in the orthogonal complement of W, the linear span of these vectors is a subspace of the orthogonal complement of W. Where are we getting this from? How do we know that this Wm plus 1, Wm plus 2 all the way up to Wn, these vectors belong to the orthogonal complement of W? That's because we know that, let's take the vector Wm plus 1. We know that this is an orthonormal basis, means it's an orthonormal set. So here any vector is orthogonal to any other vector. In particular, Wm plus 1 is orthogonal to all these previous Wy's. So automatically it would also be orthogonal to every vector spanned by these previous Wy's, naturally. But the vectors spanned by these previous Wy's form the space W. So that means Wm plus 1 is orthogonal to every vector in capital W, and that's why it belongs to the orthogonal complement of W. Similarly, the other ones also belong to the orthogonal complement of W, but now these vectors span this linear span. So if all of them are already inside a subspace, then their linear span, by definition being the smallest subspace containing them, must itself be contained in that subspace. Okay, so that's why we have this. Now we have to prove the reverse inclusion. Now let W be any vector in W perpendicular, the orthogonal complement. Then Okay, then we immediately can write something. See, being a vector in W perpendicular, after all this W is a vector in capital V, because this, just like W, this is also a subspace, it's inside capital V. So after all, this W is a vector in capital V, and that's why you are able to write W as a linear combination of all the basis elements, because this is a basis for the entire space V. And since we are not in an arbitrary vector space but rather in an inner product space, so we know what the scalars in that linear combination would be. They are the inner products. In other words, what I am saying is this: W is, instead of using summation notation, let me just write the entire thing. That way it will be more clear. Alright, but now we invoke the condition that W actually, fine, it's a vector in V, but in fact it's in W orthogonal. So that means this vector would be orthogonal to every vector coming from W. In particular, W will be orthogonal to the first MWIs, and that's why we write these things. W is orthogonal to all these Wi's. We have W, that means the first M terms would vanish and we will be left with this. But now you watch what we have achieved. We have been able to show that W is a linear combination of these vectors. So that means W would belong to their linear span. Hence, so W is any vector in W orthogonal. We have shown that it's in this linear span. Thus, W orthogonal is also contained in this linear span. M plus 1, and it is true, no? While using curly brackets, the first one is somewhat okay, but the second one becomes something like this. I recently saw a meme about this on Reddit. It is true. I mean I remembered the meme right now, so it is true, unless we are somewhat careful. See, this one is okay, but the closing bracket, it gets messed up. But anyway, so we now have achieved what we wanted. Hence, the claim that is V is the direct sum of W and W orthogonal. Well, you may ask that we have only shown that V is the sum of W and W orthogonal, but we know that these two subspaces intersect trivially. There is only the only common vector is the 0 vector. So that's why the sum is a direct sum. So that's how we have the another proof of that theorem. Okay, and this is where the solution also ends. And let me just end the video here itself. Our next upload is this coming Friday, and on Friday let's go back to calculus. So see you on Friday with that. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.